Your kids could get free or low-cost health coverage from Medicaid or CHIP. Even if you've applied before, they may be eligible now. Kids up to age 19 are covered for checkups, vaccines, dentist visits, hospital care, and more. And if they already have Medicaid or CHIP, remember to renew every year. Visit insurekidsnow.gov or call 877-KIDS-NOW. Paid for by the U.S. Department of Health and Human Services.
Hey everybody, welcome back to my podcast, Anatomy and Physiology Bit by Bit. This is your host, Dr. Steve Sullivan from Bucks County Community College, just outside of Philadelphia. Our attack on the nervous system continues today. We spent the last couple of episodes talking about nerve tissue and how it functions and its anatomy, and today we are going to move forward to the spinal cord. So we are sticking with the central nervous system right now, and we're going to talk about the spinal cord, its anatomy, and maybe a little bit about how it functions. We are moving along. I got a lot of really good feedback from the last couple of episodes getting posted, so I appreciate that. I do appreciate your comments and your nice complimentary emails, and as well as your questions. So we get a lot of good questions coming in from email, and you can email me at minus55media@gmail.com, and that will reach me, and you can ask a question, and maybe I'll be able to answer it on an episode. One of the questions I got this week regarding the nervous system came from a listener in Northern California, and his name is Isaiah. And Isaiah asked me about myelination and nerve conduction velocity. So that's a really good question, because what I didn't mention in the last episode is nerve conduction velocity, which is basically how fast the nerve signals travel along the axon. And that depends, right? So how quickly that happens depends on the diameter of the axon and whether or not it's myelinated. So we talked about gray matter and white matter in the last episode. And we also talked about what that means and the myelin sheath, right? So we had a little bit of review. We had central nervous system. Myelination comes from oligodendrocytes. And in the peripheral nervous system, myelination comes from Schwann cells. And those cells produce myelin, and they put this insulated sheath around the axon. And not only is it protective, but it also increases the velocity of the nerve signal transmission. Because when you have a myelinated axon, in between each myelin sheath, in between the cells that produce the myelin, there is an exposed piece of axon called the node of Ranvier. And that node is the only part of the axon that has to depolarize its membrane during a nerve signal. So all of those action potentials we talked about, if you have an exposed axon that's unmyelinated, every single piece of that membrane linearly has to depolarize and repolarize and have a refractory period. And that's kind of slow. So when that's how you have to transmit your signal from the beginning of the axon all the way to the axon terminals, that's a pretty slow method of nerve conduction. It's actually called continuous conduction when you have an unmyelinated axon. But in a myelinated axon, because so much of the axon is covered by myelin sheath, the ions, they diffuse through the cytoplasm, and they can get to the next piece of exposed axon much more quickly, and they only have to depolarize the nodes in between the myelin sheaths. So that's actually much faster, and it's called saltatory conduction. So when you have a myelinated axon, the nerve conduction velocity is much faster. So we think about demyelinating diseases like multiple sclerosis, right? This is a disease where in the central nervous system you have demyelination, and the myelin sheath starts to break down and wear down. And what that does is it slows down the nerve conduction velocity on those neurons. And then obviously you get a lot of neurological symptoms from a condition like that. So I hope that answers your question, Isaiah. That's a really good question. I didn't get into that level of detail in the last episode, so I'm glad we were able to bring that up and talk about the difference between saltatory conduction and continuous conduction. Let's keep those questions coming. I like seeing that, and I think it really helps move the next episode along if we've got some questions to answer. So as I record this, we are in the beginning of October. It's still October 9th for me. And, things are kind of humming along. We're still remote at my school. You're probably remote at your school, assuming you're listening to this in October of 2020. If you're listening to this way into the future, then maybe the pandemic has passed us and we're all back to normal. But right now, we're still kind of going remote, and I hope that that's something that's working for you if you're taking A&P. If you need a little extra help, I hope this podcast has helped you. But also don't forget that I've got a YouTube channel, Student Help for AP, that's the number 4. And you can check out my YouTube channel. I've got some tutor videos on there that might be helpful. And hopefully they'll help you understand some things in terms of processes that are physiological that I haven't gotten to yet in my episodes. So feel free to check that out. And then also, I have another website that I've been using to share some of the things that I've been working on lately. And that website has a lot of online anatomy and physiology materials. The URL for that website is a&ponlinematerials.weebly.com. So if I can, I will put that link in the description of this episode so you can check it out. And in there, I've got lab materials and tutor videos, things that you can take a look at and see if they help you understand some things. So anyway, I think we're ready to go ahead and move forward with the spinal cord episode. So let's get into it. All right, so the spinal cord, remember, is part of the central nervous system. It is found inside your vertebral canal, which is made up of all of the vertebral foramina stacked up inside your vertebrae. It's got a really good protection from the skeletal system in there, and also from cartilaginous intervertebral discs and ligaments that hold the vertebrae together that are adjacent to one another. And there is a 3-layer covering of the spinal cord and the brain called the meninges. You've probably heard of the term meningitis, which is an infection or inflammation of the meninges, the 3-layer covering of the central nervous system. Those 3 layers, from the outside in, like the most superficial of those 3 layers, is called the dura mater. And it is a thick, tough substance. It is made mostly of dense, irregular connective tissue. And then that dura mater is surrounded by a layer of fat and connective tissue that is between the wall of the internal vertebral canal and the dura mater itself. And we call that the epidural space. You've probably heard of the term epidural before, like an epidural injection. That means they inject a numbing agent into the epidural space. Usually they'll do that in the lower back when someone's having a baby or something like that. The next layer deep to that dura mater is called the arachnoid mater, which is kind of like a spider webby. It has no blood supply. It's avascular, and it is spider webby. That's why it's called arachnoid, like spider-like. And in between the dura mater and the arachnoid mater is what's called the subdural space. And you may have heard of the term subdural hematoma. That's when blood collects in that space. And then the deepest layer of the meninges is the pia mater. The pia mater is directly adhered to the surface of the spinal cord and brain. And then a lot of the blood vessels that supply the central nervous system are embedded in that pia mater. It holds them down to that surface. Another cool thing about the pia mater is that there are these triangular extensions of the pia mater that make like a triangle shape that look like little tiny teeth. And what they do is they extend the pia mater within the dural sheath, like the dura mater, and they extend laterally to try to hold the spinal cord in its position left and right within that vertebral column. Because remember, we're upright animals, so our spinal cord is kind of like suspended vertically in our vertebral canal, and you don't want the spinal cord banging up against the bony walls of the vertebral canal. So we have these triangle-shaped membranous extensions of the pia mater that suspend the spinal cord within the dura mater, and those are called denticulate ligaments. The space between the pia mater and the arachnoid mater is called the subarachnoid space. And these will all become pretty important when we talk more about the fluid that surrounds the central nervous system, which is called cerebrospinal fluid. So when you look at the spinal cord and you're looking at it, let's say, in a coronal section, right? So you're looking at it longitudinally, as if you've split a person, you've opened up their vertebral canal and you're looking at them from the posterior. So the spinal cord runs from the bottom of the brainstem, the most inferior portion called the medulla oblongata, and then it actually ends. It's no longer a thick cord about the diameter of your thumb around the L2 vertebra. At that point, nerve fibers continue in the rest of the lumbar spinal canal, and those nerve fibers continue downward, and they take an appearance that looks kind of like a horse's tail. And the Latin for horsetail is cauda equina, and that's what that structure is called. The cauda equina is the continuation of nerve fibers beyond the point at which the spinal cord stops at about the L2 vertebra, the second lumbar vertebra. And the spinal cord doesn't end in like a blunt, flat piece. It actually narrows down into a cone, like a triangle, and that is called the conus medullaris, and that's around that L2 area where the spinal cord starts to taper off into this cone. And then this one piece of nerve fiber, really it's actually pia mater, it's not nerve fiber, this one piece of pia mater coming down from the middle of that point of the conus medullaris continues all the way down the center of the spinal canal, all the way to the coccyx. And it anchors the spinal cord to the coccyx, and that is called the filum terminale, or terminal fiber. Now, if you look at the spinal cord, you're actually going to see it actually has enlargements in the cervical area, like where your neck is, and also in the lower part of the thoracic area of your thoracic spine. We have these two thickenings of the spinal cord. The one in the cervical region is called the cervical enlargement, and the one that takes place around T9 to T12 is actually called the lumbar enlargement. The reason for these enlargements is so that we can have nerves going to the upper and lower limbs. The cervical enlargement gives rise to nerves going to the upper limbs, and the lumbar enlargement gives rise to the nerves going to the lower limbs. Those nerves that come out of the spinal cord and go out to the rest of the body are called spinal nerves. They're on both sides. They're bilateral, and they exit the spinal cord at every segment, even where the cauda equina is. Nerves of the cauda equina will bundle up together to create these bundles of nerve fibers that leave the vertebral canal. And those are called spinal nerves. There are 8 cervical spinal nerves. So there's 8 of them exiting from the cervical spine, 12 thoracic nerves on both sides. These are pairs, 5 lumbar nerves, 5 pairs of sacral nerves, and 1 pair of coccygeal nerves. So we have 31 pairs of nerves exiting the spinal cord, and these bundles of neurons, bundles of nerve fibers, they are leaving the vertebral canal through the intervertebral foramina. Those are the holes made up of the vertebral notches of adjacent vertebrae. So you have 2 vertebrae that come together, and there's a vertebral notch on one and a vertebral notch on the other, and when they come together, they form a hole. And that hole is called the intervertebral foramina, which literally means the hole between 2 vertebrae. And the spinal nerves exit the vertebral canal through those holes. So we have 31 pairs of them. Cervical nerves, thoracic nerves, lumbar nerves, sacral nerves, coccygeal nerves. And they are typically named for the vertebral segment that they're associated with. So you have C1 nerve, C2 nerve, C3 nerve, L4 nerve, L5 nerve, T1 nerve, etc. So these spinal nerves are a combination of motor and sensory neurons bundled together to go out and innervate the tissues of your body. So there's going to be motor nerves going out to glands and muscles, and there's going to be sensory nerves coming in from sensory receptors. These are called the spinal nerves, and they are part of the peripheral nervous system. They are not central nervous system. Once they exit that spinal cord, they're out.
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
Now, the spinal nerves themselves we'll talk about in another episode. But the spinal cord, if you looked at it in a cross-section, so if you took the spinal cord out and you cut it in the transverse section and created a cross-section of that spinal cord, so you are looking at it, let's say you cut the spinal cord into superior and inferior portions, and then you hold it so you're looking at it like you're looking into a straw or a hose. That's a cross-section of the spinal cord. And you're going to notice a pretty distinct difference between the center of the spinal cord and the periphery. And the center of the spinal cord is mostly going to be gray matter, unmyelinated nerve tissue. And it looks kind of like a butterfly in the center of the spinal cord. And the surrounding periphery area is white matter, myelinated and unmyelinated, a combination of nerve tissue, and that surrounds the gray matter. You'll also notice there's a deep crevice in the anterior, right in the midline, called the anterior median fissure, separating the left and right sides of the spinal cord. And then you'll have a more shallow depression in the posterior called the posterior median sulcus, a shallow, narrow furrow on the posterior side, separating the left and right posterior white matter. So the white matter that's in the periphery is divided up into what we call white columns. These are where you'll find your spinal tracts, which are bundles of axons traveling up and down the spinal cord. And they travel in these white columns. Each side of the spinal cord has an anterior white column, a left and a right. We have lateral white columns on the left and right. And we have posterior or dorsal columns in the posterior, a left and a right. And these are where we're going to find a lot of our spinal tracts, or again, our bundles of axons carrying nerve signals up and down the spinal cord, motor signals coming down the spinal cord from the brain, and sensory signals going up the spinal cord toward the brain. In the gray matter in the center, you're going to notice that the butterfly has a body and it crosses the midline, and we call that the gray commissure. That's the centermost piece of the spinal cord. It is gray matter crossing the midline, and it has a tiny little hole in the middle called the central canal. And that central canal will run the length of the spinal cord. There's also a little piece of white matter that crosses the midline in the anterior called the anterior white commissure. So commissure means crossing the midline. Commissural fibers cross the midline. We'll see a few of these as we move on with our episodes. So that gray matter is also divided up into horns. So think of a butterfly with its wings spread out. Okay? So the body of the butterfly would be the gray commissure. And the wings will be divided into regions. Each wing will have a part that flares out anteriorly and a part that flares out posteriorly. We call those the gray horns. So the piece of the gray matter that flares out anteriorly are called the ventral gray horns. Remember, ventral and anterior mean the same thing. The ones that flare out posteriorly are called the dorsal gray horns. Dorsal and posterior mean the same thing. Now, the ventral gray horns, they are the location where motor nerve signals will leave the spinal cord, traveling out to the periphery. And the dorsal gray horns are the location where sensory nerve signals come in to the spinal cord from the periphery. So that's a really important distinction because the direction that these nerve signals take is going to be really important because spinal nerves are actually made up of two roots, a dorsal root and a ventral root. The ventral roots only have motor neurons in them, and the dorsal roots only have sensory neurons in them. But when they combine together before the spinal nerve leaves the vertebral canal, you have a spinal nerve that has both motor and sensory neurons. But sensory signals always travel into the spinal cord in the dorsal aspect, through the dorsal root into the dorsal gray horn, and motor nerve signals always leave the spinal cord from the ventral aspect, the ventral gray horns out to the ventral root. That's an important distinction. Then there's also smaller extensions right in the middle, right between those two gray horns called the lateral gray horns. And they don't really reach too far out, and they contain an aspect that is associated with the autonomic nervous system, which is what's regulating smooth muscle and cardiac muscle and glands and things like that, where you have more autonomic fight or flight type, rest and digest type things. And we'll talk more about the autonomic nervous system in a separate episode. All right, while we're at it, why don't we talk a little bit about spinal tracts? Spinal tracts are pretty important because it's the way, again, that nerve signals travel up and down the spinal cord. And the spinal tracts are located in the white columns, the columns of white matter. Sensory tracts are also called ascending tracts because they carry sensory nerve signals superiorly from the spinal cord up toward the brainstem, and the cerebellum. So we call those ascending tracts. Motor tracts are also called descending tracts because they conduct nerve signals from the brain down the spinal cord. So remember, the tracts are bundles of axons in the white columns, and they're really important to making sure that the brain can perceive sensory information. Also, so that other parts of the brain, deeper parts of the brain, like the brain stem and the cerebellum, can process sensory information, even if it's something we don't even know that is happening. Right? So think about your blood pressure. If your blood pressure has a minor increase, you don't feel that. You don't notice that. You don't feel pressure inside your arteries from that. However, your brainstem really needs to be aware that that's happening. That is a sensory signal heading towards your brainstem. Your brainstem processes that information and sends out corrective signals to bring your blood pressure back down. And that is going to be an important aspect of regulating your blood pressure with a sensory nerve signal traveling to the brain, right? Your brainstem is going to be involved. Your hypothalamus might be involved, which is another part of your brain. And those corrective signals, those feedback systems are happening beyond, or I should say below, your level of conscious awareness. So sensation doesn't always have to include you being consciously aware of what's happening. That's an important aspect. So some of these spinal tracts are not heading all the way up to the part of your brain where you can perceive what is actually happening. A lot of them are stopping. They're stopping in an area of your brain that is below your level of conscious awareness. We call that the central nervous system destination of the nerve signal, right? That's an important thing to keep in mind. The CNS destination of a sensory nerve signal will determine whether or not you actually have conscious awareness or perception of that particular event or stimulus. And we're not supposed to have conscious awareness of all of it. Think about how inefficient our bodies would work if every time your blood pressure went up a few points, you had to consciously sit there and carry out actions to bring it back down, right? Or every time your heart rate needed to change, you had to do that, like yourself, consciously, right? It's not an efficient system. We wouldn't have made it this far if that was the case. So that's an important thing to keep in mind. Not all sensation is perceived by us. Again, the motor tracts are descending. They're carrying nerve signals down the spinal cord. So don't forget that either. Okay, so when you name a spinal tract, it's actually named in an interesting way. So in the name of a spinal tract, you will have the location in the spinal cord. You will also have the part where the tract originates and the part where the tract ends. And if you know where it originates and ends, you also know the direction of that tract, which means you should be able to predict whether it's a motor or a sensory tract if you know where it begins and ends. So this is an interesting thing. Let's take up an example. The anterior spinothalamic tract. So the anterior spinothalamic tract is in the anterior white column of the spinal cord, right? And its spino is the first part of the name of the tract. So it begins in the spinal cord, and the second half of that name is thalamic or thalamus. The thalamus is a part of the brain that receives sensory nerve signals and then transmits them to the appropriate part of your brain's cortex, the outer shell of your brain, so it goes to the right spot so we can perceive that sensation accurately. So, anterior white column. Spino begins in the spinal cord. Thalamic ends in the thalamus tract. So if we know it begins in the spinal cord and ends up in the brain, we know that the direction of nerve signal movement is ascending up the spinal cord toward the brain. So we know this is a sensory tract. So the anterior spinothalamic tract is a sensory tract because we can tell from the name. So another example would be a motor tract. So we could think of a motor tract like a corticospinal tract. So if we had a corticospinal tract Cortico means cortex, which is the neocortex of the brain. Spinal means spinal cord. So we know that's a motor tract. That's a descending tract. The nerve signals are traveling from the brain down the spinal cord. So we have a bunch of tracts. I'm not going to really get into naming a whole bunch of them for you in an episode. I think that would be really tedious. But you can look them up: spinothalamic tracts, the dorsal columns, direct pathways, indirect pathways, rubrospinal tracts. We have so many different spinal tracts, spinocerebellar tracts going from the spinal cord to the cerebellum, corticospinal tracts. We have lateral corticospinal tracts. We have anterior corticospinal tracts. We have corticobulbar tracts. We have so many different tracts, spinal tracts, that I think it might be real tedious for me to just read them out to you on a podcast episode. But I'll give you one good example. So that spinothalamic tract I was telling you about, or at least one of them. The spinothalamic tracts, and there are multiples of these, they're sensory. We know that because spinothalamic, and they're going to carry nerve signals that tell our brains about tissue damage or pain, temperature changes, deep pressure, crude touch, which is poorly localized touch. Those are some of the nerve signals that travel up those tracts. The posterior columns, or the dorsal columns of your spinal cord, are also sensory tracts, and they carry nerve signals about your body's position, which is called proprioception. Discriminative touch, which means you can get enough information from sensory receptors so that you can describe an item you're touching. So imagine that you're playing a game where you have to wear a blindfold and somebody hands you an object and you have to describe it based on feeling it. You could describe its texture, its mass, its temperature. There's so many different things that you can its size. You can describe that. That's called discriminative touch. Another thing on the posterior columns is 2-point discrimination, how far apart you can feel two stimuli. Pressure, vibration, all of those things travel up the posterior columns. And then some examples of motor tracts. We have a good way to break them down is direct pathways and indirect pathways. Direct pathways carry nerve signals from the cerebral neocortex down the spinal cord so that you can initiate precise voluntary movements of skeletal muscles. That's the ones I mentioned earlier, the lateral and anterior corticospinal tracts and the corticobulbar tracts. Indirect pathways are more associated with coordinating your movements. So not so much about initiating the voluntary movement, but actually making sure that the movements that you initiate are what's actually happening in your body. So this is about coordinating skeletal muscle movement. Coordinate body movements with your visual stimuli, maintain your muscle tone and posture, balance and equilibrium, things like that. So these tracts are the rubrospinal, which comes from the red nucleus in the brainstem, the tectospinal, which comes from the tectum of the brainstem, and the vestibulospinal tracts, which comes from the vestibular region of your brain, which controls balance and equilibrium. So I gave you some examples. Again, I did give you some examples. I said I wouldn't hash it out. But again, I'm not going to read them all to you. You can very easily look these up in your textbook and get a lot of good information about them.
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
I think that's pretty good for this episode. We've gone pretty decent amount of time. So what I want to do is wrap it up and tell you that in the next episode, we'll probably talk about reflexes, specifically spinal reflexes. But maybe we'll just kind of use that time to just go overall spinal reflex arc and then reflex arcs in general, because we're going to eventually get to visceral reflex arcs as well, which are, controlling your blood pressure, heart rate, respiratory rate, things like that. So I think that this is a good place to wrap it up. I really appreciate you listening. Thanks for taking the time to learn a little bit more about the spinal cord, and I hope that this is something that's helped you out. And if you have any questions, please feel free to email me, and don't forget that website, www.anponlinematerials.weebly.com. And that will give you access to a lot of the tutor videos that I've made, as well as some lab videos that I've been producing during the pandemic, so that way students could see the dissection of a sheep brain or sheep heart, pig hearts, pig kidneys. I got a pig kidney in there, and a lot of histology too. So there's a lot of new stuff that I'm producing all the time, and I hope that that is something that can really help you be successful in this class. B or better, right? So you need a B or better in A&P to move on to nursing school. All right, have a great day, and I will see you next time. Hey everyone, don't forget to check out my YouTube channel, Student Help for AP. Student Help, the number 4, AP. There's a lot of tutor videos on there that I think could be really helpful. I also have an Instagram account and a Twitter feed with the same name. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media, with a special thanks to Bucks County Community College, McGraw-Hill Higher Education, and my family.